Hello, everyone. Pavel kicked this room off this morning by greeting everyone in Russian. I can't do that, so sorry, but thank you for having me here. This is very wonderful. So I'm going to talk to you today about live migration in LXD. So I think it's nice sometimes to tell you who I am and why do you care about what I have to say. So I work for Canonical. I worked for Canonical for about 3.5 years. And during that time, I worked on Canonical's container stack from the top, LXD to LXC, and then all the way down more recently to the kernel as well. Just a short history of LXC. LXC began kind of as a set of shell scripts in IBM. IBM had just purchased a company called Meiosis, and they were in the process of working with the guys at Virtuozzo and some other people to upstream containers functionality into the Linux kernel. And so they wrote a bunch of loosely correlating user space utilities for all of this, and LXC started initially as a set of shell scripts that was just basically a way to use these utilities. And that sort of continued that way up until somewhere in here, I don't remember exactly, Canonical decided to make a serious push into the containers world and hired Stefan Graeber and Serge Hallen to work on containers. And they sort of began at this point reworking LXC not from a set of kind of shell scripts, but into an actual C library that you could use, that was a binding that you could use to interface with the kernel to create containers and do other things. And it's probably worth noting at this point that you've heard a lot about containers, I'm sure, which is why you're all here. There's no such thing in the kernel as a container. There's no struct container in the kernel. It has this, C groups and namespaces and all of this other stuff that they use, seccomp and the Linux security modules and all that stuff. But the user space has to sort of coordinate all of that, and so the actual container object that lives in user space, and so that's what the LXC project gives you. And so the 1.0 release of LXC and the C library was complete. We continued on with that for a little while. I guess we got checkpoint restore support in 1.1 via CRIU, but then we sort of invented this new thing called LXD. And now, actually, in 2016, we released the 2.0 version of that, but it's worth noting kind of what LXD is and what the difference is between LXD and LXC. So LXD is basically a daemon, and the way that this works is the daemon exposes a REST API into which you can plug the command line tool that we wrote, but also novalxd or something you write. And then it sits on each host. LXD uses liblxc and links against it to talk to the kernel to create this container. But then it exposes sort of a higher level API through which you can do things like move containers or do snapshotting or other things like that. And I guess, so you can do snapshotting. You can also do other stuff like injection. So lots of VM hosting hypervisors allow you to manipulate the guest in some way. You can inject files or whatever. But what this talk about is in particular is live migration. So let's talk about that a little bit. The command is basically a move, and if the container happens to be running, it will live migrate it for you. But more interesting is, that's very fancy, but what actually happens when you do this, when you type LXC move. So first there's some handshaking just to make sure that versions are correct and everything. And that handshaking, you get 3 channels. One is sort of a control channel where, if some part of this process fails, you can say, hey, this failed, and send it back to the other guy, and things just continue on as they were without the migration succeeding. And then there's sort of the more interesting pieces, which are the file system piece. So in order to migrate something, you need to migrate all the files that the container could see. And then also its in-memory state. So if the container is a database and it's allocated, 10 gigs of RAM for its cache, and it has the cache laid out in some specific way, that's state that you want to preserve. So the file system state is interesting. LXD supports, I think, 5 different backends, we call them. So basically, you can run your container with ZFS, Btrfs, LVM, or just on a directory. And so the more interesting ones of these are the ZFS and Btrfs cases. These file systems offer copy on write support. But then for this case in particular, where you have a file system on one machine and you want to send it to another, they also offer this binary diff primitive. And so what that means is you can take a snapshot of a file system and say, send the blob of this file system to this other machine, and that blob is really the kernel state that you would need to recreate this, not at the the syscall level, but internally you can whatever the kernel would need to do to create that file system again. And then in particular, you can say not only send this blob, but you can take two snapshots and then say send this blob, but only send it as a diff relative to this other blob. And so the diff it's a lot smaller. And so for example, if you're doing some sort of iterative migration or something, this offers you a very nice primitive so that you can continue letting the thing modify the file system, and the amount of data you need to send each time is smaller and smaller. And then the other interesting channel is the memory channel, and we'll basically talk about this for the rest of the talk. So the way that we do this is a tool called Checkpoint Restore in userspace, and this tool is maintained by this guy standing in the back of the room, Pavel Yemelianov, and he works at Virtuozzo. And it's sort of a brainchild of the Virtuozzo, formerly Parallels, formerly SWSoft. They have traditionally had a large out-of-tree kernel patch set, and they used to do live migration between two machines via this sort of out-of-tree patch set. And they attempted at various points to upstream this functionality, but I think were rejected basically because the changes were simply too large and too invasive. So the core insight for Checkpoint Restore in userspace is that the kernel exposes a lot of information through /proc or various system calls or whatever. So it exposes a lot of information about the current state of everything for a task. And the idea is just, well, can we use from userspace, can we read all of that information and serialize it in some way so that we can then restore it on some other machine? And so this idea was posed in 2011. There was some basic kernel patches needed, and there's been progressively more as this idea has progressed. But the first kernel patches were merged around then, and then CRIU sort of progressed from there, as you can see, into sort of where we're at today, which is there's support merged in Docker, there's support merged in Virtuozzo, and if you're using the Virtuozzo 7 product, you're using this to do live migration. And then also LXD, Canonical offers a supported version of this as well. Yeah, so it's pretty cool, except for, of course, there's a catch. Every talk must have some funny quotes. This is a funny one. This is from Linus, the commit logs. He says, a note on this. This is from the first time that anything was merged. A note on this. This is a project by various mad Russians to perform checkpoint restore mainly from userspace with various oddball helper code attached, added in the kernel where the need is demonstrated. However, I'm less confident that the developers than it will all actually eventually work. And so there's a kernel config called config checkpoint restore, which is all of the stuff is guarded by. So the question is, how does this actually work? So I just took this last night as this is a Zesty container, so the next release of Ubuntu will be Zesty. And so when it's starting up, we use systemd, so it runs sbin init. This process at the top here is just the orchestration mechanism. It's a watchdog for the whole container, and you can talk to it to ask it to do stuff. So the real container starts right here. And then there's some other systemd processes. There's a zombie. I captured this right as it was booting, so systemd hasn't reaped this zombie yet. And then it looks like it's loading it's probably doing some systemd units here. There's an AppArmor one and an EBTables one. And then this bottom thing is a cloud init, which is a thing that we run in Ubuntu to make it easy to configure cloud instances. So this is a pretty typical something you might see in a container. And the idea is that you want to recreate this process tree and all of its state and the whole thing on some other host. And so basically the way CRIU works is it tries to capture all of the state. So we heard a nice talk again from Pavel this morning about debuggers. We use the ptrace interface to inject some code into the process's address space and run it to collect various things that aren't available anywhere else. For example, you can't tell from outside the container what the cgroup namespace path it's in, and so if there's some cgroup namespace prefix, the only way to know is to look from inside the container and compare that to your reality outside the container. And so there's a lot of different things like this where the various pieces of information that you need are only available to things inside the container, so you need to inspect the container itself. Like open FDs, for example, some task might open an FD and seek to some particular offset. And if you want to recreate the whole process's state, you need, when you restore, to reopen that FD and reseek to that offset and everything. So there's some stuff that's done from inside the container, some stuff that's done from outside the container. But basically, you grab all of the state that is available and you save it to some on-disk format. CRIU uses protobufs and some other raw file formats to serialize everything, and then you restore. And so what does that look like? Well, if you think about what needs to happen, the init system forked 6 times because it has 6 children. And then even though the init system didn't do this, your host sees the process title as init, so we need to preserve that to state. So you need to do the set proc title, and then also it may have opened some other file descriptors or done other things. These other 2 services also need to preserve their process titles, but then like systemd journald, it binds to a Unix socket so that other processes, like when you run a journalctl status, it talks to this journal daemon over this Unix socket to get the actual information. So then you need to, when you're restoring this task, you need to do that bind. There's some other stuff. This one was a zombie, and so it doesn't really do anything, but you need to preserve the process title, and then you just exit. Tasks with children need to fork. Everybody, has some memory that they have mapped, usually via the loader. So for example, if you load a libc and maybe you load a libseccomp, or I guess in this case it would be libaparmor, you mmap that shared object off the disk and into some particular memory location. So CRIU needs to record all of that stuff and then mmap the same objects off the same file system into the same location on disk. There's stuff like session IDs. So this was a bash process. It might do set session ID, and so you need to fork set that session ID. But you might have to do this the other way. For example, if the task did it the other way, if the session ID of these 3 match, then you'd want to do this before. And there's some other stuff. This uses EB tables, so it probably opens some netlink socket to talk to the kernel about what EB tables does, and then maybe it does a set UID, so it can't open more netlink sockets. So basically, you can see this is sort of a real big rabbit hole where everything that you can do via a syscall, somebody has to sit down and think about, how can I redo this? First of all, how can I capture whatever state is in, whether the socket's in a particular state or whatever. And then also I need to figure out how to restore it to that particular state. So if there was a netlink message that was half sent or something like that, we have to do all that. And then there's actually another problem. Even if you have all of those primitives, you have to do them in the right order, because you have to figure out, do I fork or do I set a session ID first? Once I set UID to something that's not root, there's a lot of operations that I can't do. So I need to be sure and do all of the operations that root requires before I do a set UID to non-root. And so I think I think you can talk to Pavel and get a PhD if you can figure out the answer to how to do that. Right now we have a bunch of heuristics, and it seems to work for most applications, but you can definitely write containers that do things that we don't know how to checkpoint restore. So there's a lot of things that we don't necessarily know how to do, and so about a year and a half ago, there was a thread, maybe a little longer, I guess. There was a thread on systemd devel about, can we add this to systemd? And Leonard said, no, this is not an enterprise feature. It's a promise we cannot keep. We will not add code to systemd that works often but not always, and CRIU is certainly of that kind. So, the problem is that you're always going to be playing catch up with the kernel as people add new kernel features. They won't necessarily send patches to CRIU to be able to checkpoint that. And even further, actually, people add new kernel features all the time where there's no real way to either inspect that state or restore it to a previous state. So Leonard's sort of right. We're always playing catch up with the kernel developers, and it's unlikely that there will be a mandate for, hey, this has to be checkpoint and restorable, and it's further unlikely that people will be willing to send patches to the userspace utility when they do something fancy and new like this. So it's a reasonable criticism of the approach. There's also things like this. There's when I did some patches for seccomp support for this, one of the things is when you inject code into a process's address space, it might try and open some files, or it might try and do some other operations. And the problem is you can install a seccomp policy that will block those. And so then your injected code, which isn't the real application was behaving fine, but your injected code causes the task to get killed. And that's obviously very bad because then you can't checkpoint it. So you need some temporary way to turn off seccomp. And the maintainer didn't like this, which is reasonable. So there's a lot of just little, I guess as Linus put it, various oddball helper pieces that you need to get this to work. There's other stuff that just nobody understands. So can we refuse dumping SE Linux until somebody actually understands how to do it? So initially this was implemented. I implemented support for SE Linux, which is I just did what I know how to do. But he asked me, do you understand SE Linux? No, I don't understand SE Linux. So does anybody understand SE Linux? If somebody out here understands SE Linux, come talk to us. We can do. So there's a lot of problems here with just the kernel's complicated, the interface is big, you have to do things in the right order, and all of those things are very big problems. There's lots of it, I guess is the point. But we have some smoke and mirrors, and you'll see, you can find these videos on YouTube. There's a picture of my ugly mug, and I did a live migration demo of Doom while it was running in a container, and then the Docker guys one-up me with Quake. So it does sort of work, or it does work, in fact, because we can do stuff like this, which is pretty cool. And we're offering it as a supported product, so there is some some things that are happening there. So there's some other work going on. Just to highlight, we were at Linux Plumbers 2 weeks ago talking about stuff. Task diag work by Andre Vagan is a big one. So one of the things is CRIU inspects the /proc file system a lot to get where various files are, what is this task a zombie, is it not a zombie? All of that information is in proc. What are the kernel what does the kernel think the offsets are for the command line and things like that, and a whole bunch of other just there's a ton of information in proc, and CRIU has to open a lot of these files in order to figure all that out. The problem is, for example, if you have a container with 50 processes in it, there's maybe 40 files or something in proc that you have to open. So you have to do that for each container. So 40 times 50 is 200, I think, if I did my math right. And then, but you actually have to open that and then read it and then close it. So then that's another. So that's 600 system calls you have to make to inspect all of this information from each task, or from each container. And the problem is that the container might potentially be down while you're doing this. So task diag is basically a way, the way that we do inspecting for network stuff. The modules are all called _diag. So this is basically an homage to that. But the idea is that there's just a binary protocol that you can talk to the kernel, so you have to do it once, and then you can do all of this a lot faster than having all of these system calls and having to trap back and forth all the time. AF Unix and the SCM stuff. So this is an example of just something that doesn't exist right now. If you have you can open a Unix socket and send a file descriptor over it. CRIU just doesn't know about that. And so if you restore a task with a message in the queue that has a file descriptor attached to it, that will just be gone. And your application will be very sad. So that's support that I think we talked about. I don't know what the plan is for working on that. User fault FD, this is a very interesting one. So I talked a little bit earlier when I was talking about storage about you have this iterative thing where the idea is, at least for storage, you send smaller and smaller deltas until you finally decide, okay, the delta's small enough, I can just migrate. You could do a similar sort of thing for memory, and actually CRIU has support for this, and that was the memory changing tracking patches in the kernel were merged in 2013, and so basically you can say, hey, keep track of which pages are dirty. I will send the whole page set over to the new host, and then I'll ask the kernel which pages were changed, and then I can send that smaller subset of the pages. And the idea is, again, you get the same incremental feature where eventually you decide, hey, we're going to migrate this now because we're done. The delta is small enough. But user fault FD offers another solution, which is called post copy in some parlance, which the idea is that you can actually just migrate the container, just do it right away, and then you configure it and you say, hey, if there's a page fault in any of these tasks, call out to this user daemon. And then that user daemon, when there is a page fault, then that user daemon does a TCP connection to the old host and says, hey, what was the page? And then the old host sends the content of the page over, and then user fault FD replies and says, hey, here's the content of the page that you asked for. So the idea here is just it's another way to minimize downtime. And there's been a lot of measurements by a lot of people, especially the VM guys over the years, about what situations you use pre-copy in, what situations you use post-copy in. And there's a lot of analysis on that. And so I think the conclusion there is, in most cases, you can't really tell. Like for the general case, what's going to be faster. You may end up, in this case, having to send a lot more memory than in this case. So you need to have all the options available if you want to truly implement fast live migration. So this is work basically towards that. Hopefully there will be work on supporting more LSMs, maybe SE Linux. But other than that, I think other than AppArmor and SE Linux, there is nothing. There's no other LSM is really understood by CRIU. And then there's also the ptrace option to suspend this setcomp support that the maintainer didn't like was called ptrace suspend setcomp. And we have actually the same problem with the Linux security module. So your Linux security module could say, hey, this task can't open Unix domain sockets anymore. And so when CRIU injects some stuff and then tries to open a socket to send the result back, the task can get killed by the LSM instead of setcomp. So it's exactly the same problem. It's just this different security subsystem. So if I come back next year, maybe I'll have another quote from a different maintainer that says the same thing, like this gives me the creeps. Netlink is a big one. For those of you who don't know what Netlink is, you basically can talk to the kernel and ask it various state about the crypto API. You can ask it about routes, things like IP. If you're familiar with the IP Route 2 package, this all talks Netlink to talk to the kernel about what's going on. We have support for Netlink sockets, but if there's somehow data is queued or something happens, it kind of falls over. And so one of the things would be to implement support for that. There's some patches, I guess, for this. So who knows, maybe we'll have that done too. One of the issues is that, for example, when you suspend the container, you ptrace attach to it and put it in ptrace stop, and then it just sits around. And so if you do something to, say, cause a kernel event, like, for example, CRIU might load a kernel module, and then the kernel might notify the container because it was listening on there's like a K event U object or I forget what it's called. But there's some Netlink API where you can say to the kernel, hey, notify me about events, and one event is a module. The task is sleeping, and the module gets injected, and this event is now in the kernel side buffer, and since we don't know how to checkpoint kernel side buffers, those events and things are lost. So that's another just thing that might be implemented sometime in the near future. There's also another initiative that is interesting, which is basically p-hall for Go. So p-hall is this thing that people that Virtuozzo guys wrote basically to do iterative migration, and it's what they use in their product now. But a lot of container engines are written in Go. Rocket runs C and Docker, and p-hall is written in Python, and it makes sort of coordinating all of this kind of a big headache. So we may do something along those lines too. So if you're interested in this, that may be something you're interested in doing. So the hope is to get, everybody always, there's a joke, you can either do one thing or the other thing and you have to pick one. So the hope is that someday we'll get to correct and fast with both of them, but there's a lot of work to do. So help is welcome. Just general administrivia. There's both of the projects have a month-long release cycle. They're very active. There's lots of stuff going on. And with that, if anybody has any questions, I'd be happy to answer them.
Hello. Thanks for the great talk. I have a question. As I assume that when you have some persistent network connection from the container to some external service, you just lost it. And say if I have two containers, ideally on different hosts, about at least the same host, could I move them together and without losing the connection?
So your question is about containers talking internally to each other?
Yeah.
Yeah. So much the same way as a regular TCP connection from the outside. Since the containers are probably isolated, or I hope they are isolated, they were probably talking TCP to each other, and so that's fine. Those will just migrate, and CRIU preserves, it tries to preserve the MAC address and everything. So I think the idea is that the kernel will do all of the management of that for you, and as long as you restore these within the TCP timeout window, the connection should be preserved. There's another interesting bit, which is if they were talking over a Unix domain socket, say, or you had something that was bind mounted from outside of the container inside of the container, that could be potentially a little bit more complicated. So CRIU has, this happens all the time, where you have something from the outside world that you want to put inside your container, whether it's a file system or a Unix socket or something. And so CRIU has or another example is like an actual network. So you have a VETH pair, one side's inside the container, the other side's outside, and it's plugged into a bridge. And so this concept of stuff crossing the container boundary happens a lot. And there's a mechanism in CRIU to deal with this, but your applications in some sense still have to understand that, hey, I was talking to something in the outside world, and that thing needs to understand that these connections could be interrupted or something like that. So the outside-inside case requires a little bit of coordination from the outside world, but it can be done. And actually, we have a socket in LXD that you can use to talk to the LXD API from inside the container, that we have exactly this problem of the socket is bind mounted inside, and this is how we do it. So other questions?
How do you feel? Is it fairly reliable?
We offer it as a product, and if you have, there's certainly customers. Yeah, and we certainly have customers who've asked us, like, we want to do this or we want to do that. My feeling is when it works, it will work. Meaning the code itself is I think okay, but obviously there's bugs, but there are definitely whole areas of the kernel that we just have not implemented support for. So if your application or your workload or whatever uses some area of the kernel, then somebody needs to sit down and figure out, how do I do this? So I think the claim is when it works, it will work very well. It's just, will it work for you? I don't know if that answers your question. Probably not, but.
A follow-up question. When will it most likely fail?
So basically in this case, when there's some kernel resource that it doesn't know about. And today it's pretty good about telling you, hey, there's a kernel resource that I don't know how to checkpoint. I talked a little bit earlier about the SCM credentials and stuff. When you're sending Unix sockets, it actually doesn't fail in that case. It just continues on and nothing happens. So there is a danger here where there's like a correctness problem that's very real that we don't know how to diagnose. But I would say in most cases, usually it's just, hey, we don't know how to do this and it fails. There's also a relatively recent option called check only, which you can say, hey, CRIU, go check this container and see if you understand how to restore, checkpoint and restore everything. And so you can ask ahead of time, is this going to work, basically? And then there's another thing where you can keep the container that you're migrating suspended so that if the restore fails or something goes wrong in that process, then you can just resume that container like nothing ever happened. Obviously there will be a few seconds blip or whatever, yeah, so hopefully if it fails, we can tell you ahead of time, I guess.
More questions? Okay, thank you, Tycho.
Thank you.